Welcome to the next video in Discrete Math. This is video 2.1. It's on proof by induction. It corresponds to chapter 1, section 1 of the textbook. So in the previous video, we claimed with good evidence that the recurrence, which is given by t sub 1 is equal to 1, and then for every n after 1, we have that t sub n is, or sorry, this should be, this is right. Yeah, that t sub n is equal to 2tn minus 1 plus 1. And we claim that this was solved by the formula t sub n equals 2 to the n minus 1. We had good reason for stating that, but it wasn't a formal proof, and that's what we're interested in, right? After all, mathematicians are always interested in formal proofs. If we're going to prove something that has to do with a recurrence relation, then the natural way to prove it is to use induction. And if you've never seen induction, induction always goes by having a base case and an inductive case. Now, the base case is always considering the smallest possible value for the index n. In our particular situation, we're taking the smallest index n to be 1. I think that might be in some disagreement with the book. I think the book went all the way down to 0, which is fine, right? It doesn't really matter. A lot of the ideas will be basically the same, but maybe it'll be good to see some slightly different approach to the problem. But in any case, right, I'm going to take my base case to be n equal to 1 because that's all I'm making this claim for is n starting at 1. And in order to confirm the base case, we need to confirm that what we know about t sub n when n is equal to 1 matches what we know about the formula when the formula has n set equal to 1. Well, we know just directly by what we've already just by the definition of what we're taking this t sub n to be, we know, because it's just one of the, the conditions about t sub n is that when n is equal to 1, then we're getting the value 1. So we know that about t sub 1, that it's equal to 1. If we apply n equal to 1 to our formula, which is 2 to the n minus 1, then we're effectively computing 2 to the 1 minus 1. Now, if you compute that, you get 2 minus 1, which is equal to 1. So yes, in fact, everything here is equal, and that confirms what we needed to confirm for the base case. Next is the inductive case, and this is usually a bit trickier, but the idea behind the inductive case, if you've never seen a proof by induction before, is that we assume that the claim holds. So in this particular case, what that means is that we assume t sub n is equal to 2 to the n minus 1 for any n which is at least 1. And then what we would like to prove, right, so maybe I'll make this as kind of a note, right, because we don't have it yet. So we need to prove that t sub n plus 1 satisfies the claim. And in this particular case, t sub n plus 1 satisfying the claim would mean that like this whole formula works when n is set to n plus 1. Now, let's just comment for anyone who hasn't seen a proof by induction before, why is this valid, right? Why is it that when you establish the base case and then you also establish the inductive case, then it follows that the claim is true for every possible choice of n? Well, the idea is that this, base case kind of establishes that the claim is true for n equal to 1. So I guess let's just kind of annotate that by saying when n is equal to 1, by confirming the base case, we get a check mark. We know that the claim is true for when n is equal to 1. Great. What do we get from the inductive case? We basically prove in the inductive case a conditional sentence, right? This tells us that if the claim is true or proved for any choice of n, then it follows that it will also be true when we set everything to n plus 1, right? So this gets us kind of a transitional principle or proposition or something, right? It's a conditional. It says if it is true for n, right? We assume that it is true for n, so if it is true for n, then it must follow, right? This is what we will prove next, is that it follows from that the claim is true for n plus 1. And that's true no matter what n is set to. So in particular, if we set n equal to 1, then by this kind of transitional principle, it follows that the claim must also be true for n equal to 2. And then now that we know that the claim is true for n equal to 2, again applying the transitional principle, this time when n is equal to 3, then we get, or sorry, with n equal to 2, that we get that it follows that the claim is also true when n is equal to 3, and so on, right? So that's the principle, that's the idea behind why proof by induction is valid. The base case gets you a starting, certainly true foundational, sort of like point to start this whole thing off. But then the inductive case tells you that whenever it is true at n, it must therefore also be true at n plus 1, and it gets you this, right? It tells you that everything after that must also be true. So anyway, returning to the task at hand, then what we are trying to do is we are trying to assume that the claim is true for n, where n is any number at least 1, and prove that it must follow that it is also true for tn plus 1. So let's start from what we know about tn plus 1. Notice, right, that's where we're starting, and this is where we would like to end. We would like to prove that tn plus 1 is equal to this other expression, 2 to the n plus 1, all minus 1. But what can we actually say about tn plus 1? Well, by knowledge of what defines tn and tn plus 1, then we can apply this, right? This would tell us that tn plus 1 is equal to 2tn, right? Because here, this would be n plus 1, this would be n plus 1, and then this whole subscript here would just simplify to n. So let's go ahead and write that. So tn plus 1 must equal 2tn plus 1. So this we just know by the defining properties of this sequence t sub n. Next, what can we say? Well, we are, right now assuming that the inductive hypothesis holds, namely that t sub n must itself equal 2 to the n minus 1. That's the assumption for the inductive case. So we can then do a substitution, right? We can replace tn with what we are assuming it is equal to, which is 2 to the n minus 1. So we get this. And there we have it, right? So after that, I just do a bunch of very natural algebra. So this is substituting tn with 2 to the n minus 1. So that's applying the inductive hypothesis, right? Namely this assumption right here. And after distributing 2 in, then 2 times 2 to the n is 2 to the n plus 1. Here we get a minus 2. This plus 1 just carries over. We simplify the minus 2 plus 1 into just a minus 1. And this is exactly what we said we needed. So that's the end of the inductive case, right? So this assumption right here, we often call the inductive hypothesis. Let me go ahead and write that here. So that is often called the inductive hypothesis. So that is what we assume in the inductive case, right? The inductive case is this entire component or portion of the proof. That's the inductive case. The assumption that we make is often called the inductive hypothesis, and it is always that the thing we are trying to prove is true for a given arbitrary n. So that, right, the thing we are trying to prove is tn equals 2 to the n minus 1. So we assume that that is true for n. And with that assumption in hand, we then use it to prove that the claim is true for n plus 1. And so, so here it is, right? So I hope that makes sense. If you have any questions, please leave a comment. But since that concludes the inductive case, then the entire proof is done, right? So a proof by induction always has a base case and an inductive case. And once you've established both of those, the proof is complete.